Galaxies are vast collections of celestial bodies, dark matter, gas, and dust. The dark matter in galaxies keeps the matter in galaxies together. Otherwise, in the outer reaches of galaxies, matter would be easily lost in intergalactic space in large amounts. They are gigantic in size, ranging from thousands to millions of light years in diameter, the largest being IC 1101 with a diameter of about 4 million light years and a mass of about 100 trillion stars. Milky Way is about 100,000 light years wide and contains about 250 billion stars. The closest galaxy to the Milky Way is the Andromeda Galaxy, which is about 220,000 light years with about 1 trillion stars. Galaxies are mostly found in clusters and superclusters, which are basically vast and huge collections of galaxies. Clusters are made up of galaxies, and superclusters are made up of clusters. The Milky Way galaxy resides in a galaxy cluster that is called the local group, which is in the Laniakea supercluster. There are about 30 galaxies in the local group, and about 47,000 galaxies in a neighboring cluster called the Virgo cluster. The Laniakea supercluster has about 100,000 galaxies and stretches out for about 520 million light years. The three biggest galaxies in the local group are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Dark matter. Dark matter plays an important role in galaxies. Dark matter is currently speculated to keep matter in galaxies gravitationally bound to the galaxy, keep galaxies in clusters, and keep clusters in superclusters. We do not know what exactly dark matter is. The matter inside galaxies is the water in a water balloon, while the rubber balloon that keeps the water together is the dark matter. We know that it exists because we can see the gravitational effects of dark matter. Dark matter is currently undetectable by current technology because it does not interact with the electromagnetic force. This means that it does not interact with radiation. All things in space are identified through electromagnetic radiation. We identify the sun through visible light and ultraviolet radiation. The sun emits energy in the form of electromagnetic radiation because it can't store the energy that is being produced due to fusion. It can hold only so much energy at a time. Most animals emit infrared light, which is captured by the infrared cameras and then converted to visible light so that we can see the frequencies or the concentration of the infrared waves in the animal. Like this, all matter after one point emits energy. In this way, we can identify celestial bodies. But since dark matter does not do so, we can't detect it. We know that dark matter is non baryonic in nature. Baryons are particles like quarks and the things that are made up of quarks. There are six types of quarks: up quarks, down quarks, strange quarks, charm quarks, top quarks, and bottom quarks. Stable matter like protons and neutrons are made up of up and down quarks. So dark matter doesn't interact with each other or with normal matter like nuclei, which emit and absorb radiation. Classification of galaxies. Galaxies are categorized into six main categories, which are elliptical galaxies, spiral barred galaxies, lenticular galaxies, intermediate galaxies, and irregular galaxies. The most widely used model for classification of galaxies is the Hubble-Vacuolar tuning fork, which was made by Edwin Hubble and further modified by Gerard de Vacuolar after more discoveries were made. As we move across the tuning fork from the left to right, first there are elliptical galaxies, and then there are lenticular galaxies. After lenticular galaxies, there are spiral galaxies, spiral barred galaxies, and intermediate galaxies. And outside of the tuning fork, we have irregular galaxies, spiral galaxies. Spiral galaxies consist of a galactic nucleus, a disk that contains the spiral arms of the galaxy, a galactic halo which has a stellar halo, and a dark matter halo. The galactic nucleus in spiral galaxies is spherical in shape, and the size of the galactic nucleus decreases and the openness of the spiral arms increases as we move across the tuning fork from left to right. The galactic nucleus is also known as a central bulge. The central bulge in smaller galaxies is concentrated with stars, gas, and dust, and in larger galaxies with gas, dust, stars, and a supermassive black hole. The spiral arms of the galaxies have the highest concentration of gas and dust, and have the highest rates of ongoing star formation due to the high concentration of gas and dust. The clouds of gas and dust collide together, which compresses the matter at the shock front. The shock front is the area of the clouds which collides with the other clouds. The compression of huge amounts of matter starts nuclear fusion, which forms lumps. which attracts other matter due to gravity and then becomes stars. The black holes in the centers of galaxies are gigantic. The black hole in the center of the Milky Way is about 4 million solar masses. One solar mass is equal to the mass of our Sun, which is about 1.98 into 10 raised to the power 30, which is 198 followed by 28 zeros. In some galaxies, the black holes are active, which means that they are currently sucking up huge amounts of matter. The matter near the black hole rotates at speeds close to the speed of light, which emits high amount of radiation in the electromagnetic spectrum due to the heat produced by the friction. The kinetic energy and the heat energy is converted into electromagnetic energy. These celestial bodies are extremely luminous and are known as quasars or blazars. Spiral bar galaxies. Spiral bar galaxies consist of a galactic nucleus, a disk that contains the spiral arms of the galaxy, a galactic halo which has a stellar halo, and a dark matter halo. The galactic nucleus in spiral bar galaxies is elongated in shape like a bar, hence the name. Like spiral galaxies, the size of the galactic nucleus decreases and the openness of the spiral arms increases as we move across the tuning fork from the left to right. Also, they too have high concentration of gas and dust in their spiral arms, which leads to high rates of ongoing star formation in the spiral galaxies. Intermediate galaxies. Intermediate galaxies are galaxies which are in between spiral and spiral bar galaxies. Intermediate galaxies too consist of a galactic nucleus, a disk, a galactic halo, which consists of a stellar halo, and a dark matter halo. They have a central bulge which is spherical and barred at the same time, and the spiral arms have similar characteristics to the spiral and spiral barred galaxies. The size of the central bulge and the openness of the spiral arms changes as we move across the tuning fork from the left to right, the same as spiral and spiral bar galaxies. The intermediate galaxies too, like spiral and spiral bar galaxies, have high concentration of gas and dust in their spiral arms, which causes the rates of star formation to be high. One of the signs that star formation is going on is that the gas clouds nearby glow blue and pink because heated hydrogen emits blue and pink light. Elliptical galaxies. Elliptical galaxies are basically ellipses which contain older stars than spiral, spiral barred, and intermediate galaxies. Elliptical galaxies have small amount of gas and dust compared to spiral, barred spiral, and intermediate galaxies. Due to the small amount of gas and dust spread out over a large volume, and the gas and dust absorbing energy from high number of stars, gain a high amount of kinetic energy, which generates random motion, which makes it hard to compress the gas and dust to form stars. Rates of star formations are near zero. Elliptical galaxies in the Hubble-Divacular's tuning fork are classified in order of increasing ellipticity from left to right. The ellipticity of elliptical galaxies is determined by the formula E is equal to 10 parentheses open 1 minus b upon a parentheses closed. In E0 galaxies, E is equal to 0. In E3 galaxies, E is equal to 3, and so on. E0, E3, E5, and E7 are the most common magnitudes of ellipticity found in elliptical galaxies. The largest galaxies in the observable universe are elliptical galaxies. Large elliptical galaxies have black holes at their centers, which keeps the galaxy gravitationally bound. These galaxies, too, like others, have dark matter in them, which keeps the galaxies together. Lenticular galaxies. Lenticular galaxies are in between disk galaxies and elliptical galaxies. Disk galaxies are basically galaxies that have a disk, like spiral galaxies, spiral barred galaxies, and intermediate galaxies. Lenticular galaxies have a central bulge which consists of stars, gas, dust, and black holes, which merges into the smooth disk that is made up of older stars due to the lack of gas and dust. The low amounts of gas and dust mean that the rates of ongoing star formation in lenticular galaxies, like elliptical galaxies, are very low. These galaxies too have a stellar and a dark matter halo. Irregular galaxies. Irregular galaxies are galaxies that have no definite shape. These galaxies can't be classified into any of the five categories mentioned above. Examples of such galaxies are the Large and Small Magellanic Clouds, which orbit the Milky Way, and the Antennae, which is an irregular galaxy, which is basically two galaxies in the process of merging. Further classifications. There are further classifications for galaxies. They include starburst galaxies, quiescent galaxies, and galaxies with quasars or blazars. Starburst galaxies are the galaxies that have a high rate of ongoing star formation. Starbursts in galaxies are usually triggered by mergers or by other gravitational interactions that cause the gas clouds in the galaxy to collide with each other. Quiescent galaxies are galaxies with an extremely low rate of star formation, which is very close to zero stars, like elliptical galaxies. But unlike elliptical galaxies, these galaxies aren't bright and are very hard to detect. Galaxies containing quasars and blazars. Quasars are the same as blazars, except that the angle at which we see the celestial body differs. Quasars and blazars are active galactic nuclei. This means that they are actively feeding black holes which are ingesting and are surrounded by a huge amount of matter which is moving at speeds close to the speed of light. This causes a huge amount of friction, which produces a huge amount of energy and is mostly emitted through electromagnetic radiation, mostly in higher frequencies like gamma radiation, microwaves, etc. The active galactic nuclei emit jets of electromagnetic radiation, which makes them very bright. Whether an active galactic nucleus is a quasar or a blazar depends on the angle of the jets to us. If the jets are directed very nearly to us, then it is a blazar. Otherwise, it is a quasar. Formation of galaxies. Protogalaxies are also known as primeval or primordial galaxies. These galaxies are galaxies that are formed through contraction and condensation of large gas clouds. The gas clouds of the young universe were made up of mostly hydrogen and helium. There also was dark matter around and inside the gas clouds, which kept the gas together in sort of a bubble of dark matter. The particles in the gas clouds collided with each other, losing energy in the process and then moving towards the gravitational center of the gas cloud. The protogalaxy now has a very thin and small halo of gas and a large halo of dark matter, as dark matter doesn't fall into the center as it doesn't interact and lose energy in the process like normal matter does. The protogalaxies merge. In the process of merging, the thin halo and the core of gas of the protogalaxy collides with the thin halo and the core of gas of the other protogalaxy, which creates stars. Here too, as discussed earlier in the video, rates of star formation are highest at the shock front of the collision, where matter gets most contracted and condensed. If the amount of star formation is very high, most of the stars form in a few bursts at the beginning. The rest of the gas and dust scatter due to absorbing energy, which reduces the rates of star formation to near zero. The galaxy then becomes an elliptical galaxy, which consists of older stars and less gas and dust, but still has a dark matter halo. If we plot the rates of star formation in the merger for elliptical galaxies, it will look something like this. The rates of star formation skyrocket in a large burst and then drop to near zero levels. When the protogalaxies merge, and the star formation happens slowly and is stable, then the amount of gas and dust in the galaxy is high, and the galaxy becomes a spiral galaxy, which develops a disk of gas, dust, and celestial bodies, along with a halo that has a stellar halo and a dark matter halo. If we plot the rate of star formation for this type of merger, it will look something like this. The rates of star formation increase and stay at similar levels for a very long time. Elliptical galaxies are also formed when spiral galaxies merge. Merging of spiral galaxies causes the star formation to increase in one large burst. When the spiral arms collide, the star formation takes place at the shock front as the spiral arms of the spiral galaxies have the highest concentration of gas and dust clouds. The rates of star formation then decrease as the galaxies become one large elliptical galaxy. Due to the high rates of star formation, the remaining gas and dust either adds up to the stars or it scatters due to absorption of energy produced by the existing stars and the formation of stars. This causes the galaxy to become an elliptical galaxy. After about 4 billion years, the Andromeda galaxy and the Milky Way galaxy will collide and merge, which will result in the galaxies becoming one large elliptical galaxy, which has been named the Milkomeda by scientists. Lenticular galaxies are formed when galaxies like spiral galaxies, spiral barred galaxies, and intermediate galaxies undergo a starburst. But there is still some gas and dust left that forms the disk along with other celestial bodies. Lenticular galaxies aren't formed only because of starbursts. If the gas and dust in a galaxy slowly depletes, but not very low like elliptical galaxies, then the galaxy becomes a lenticular galaxy. If the amount of gas and dust were lower, the galaxy would become an elliptical galaxy. There also are irregular galaxies, which are created through gravitational and or physical interaction with other galaxies. A galaxy, which is called the antennae, is basically two spiral galaxies in the process of merging. Two more examples are the Large and Small Magellanic Clouds, which are irregular galaxies that are orbiting the Milky Way. These galaxies are becoming a part of the Milky Way, as they over millions of years will slowly merge into the Milky Way. Note that this merger is not a major merger and will not change the shape of the Milky Way or will affect it so radically that it becomes an elliptical galaxy. Because the Magellanic Clouds are incredibly small galaxies, they are also known as dwarf galaxies. This model of galaxy formation has a lot of great evidence. Galaxies can help us see in the past. Imagine you are in a field with a length of 300 meters. You are at one end and there is a light source at the other end of the field which you can see. The light source that you are seeing is as it was 1 microsecond ago or 1 millionth of a second ago, as it takes some time for the photons to reach your eyes. So, if a celestial body is situated about 10 light years from us, we are seeing it as it was 10 years ago. Using this method, astronomers have gazed into the faraway clusters and have found high amounts of spiral galaxies, and in nearer clusters, they have found high amounts of gigantic elliptical galaxies and irregular galaxies. This supports the notion that spirals merge to form elliptical galaxies and that irregular galaxies are either galaxies in the process of interacting with each other physically or gravitationally. Measuring intergalactic distances. There are two main methods that can be used to calculate intergalactic distances: the standard candle method and the spectroscopic shift. The standard candle method is like using one celestial body as a reference to calculate the distance. Imagine you have a candle 3 meters away from you. The candle is lit, and you know the approximate luminosity of the candle. You can calculate the distance between you and the candle by using the apparent brightness of the candle to you and the distance that you are from the candle. We use the inverse square law to calculate the distances. The inverse square law says that the apparent brightness is inversely proportional to the distance squared. Think of it like this: you keep a screen with an area of 1 centimeter squared at 1 meter from the candle, and you measure the number of photons. Suppose it's 1 billion photons. You move the screen 1 meter further away from the candle. There will be about 250 million photons. If you move the screen 1 more meter away, the number of photons will decrease to about 111 million photons. The number of photons at 2 meters from the candle on the screen were about one fourth of the number of photons on the screen at 1 meter. The number of photons on the screen at 3 meters from the candle were about one ninth of the number of photons on the screen at 1 meter. So, we can say that the apparent brightness equals luminosity divided by distance squared, where r is equal to the distance. This same method is used to measure the intergalactic distances. There are stars called Cepheid variables, which are thousands of times more luminous than the Sun. Cepheid variables are stars that have a cycle, where the luminosity of the star predictably changes before returning to the starting point. We know the intrinsic brightness, which is basically the luminosity of the star based on its mass, which is determined by the period of its cycle. Once we know the intrinsic brightness of a Cepheid variable, we can use the inverse square law to find out the distance between us and the galaxy where the Cepheid variable is situated. Another standard candle that we use are type 1a supernovae. These supernovae are extremely bright and can be detected and seen through telescopes millions of light years away. This type of supernova occurs when a star in a binary system goes supernova, and when one of the stars is a white dwarf. When the stars come close enough, the white dwarf attracts matter from the other stars, and then when the matter stolen from the other stars on the white dwarf reaches 1.4 solar masses, the white dwarf explodes, leaving nothing behind in a type 1a supernova. The luminosity of a type 1a supernova is about 5 billion times that of the Sun. Once again, using the inverse square law, we can calculate the distance between us and the galaxy where the type 1a supernova is taking place. The other method that we use to measure intergalactic distances is called spectroscopic shift. This method is based on the Doppler effect. The Doppler effect is when the waves emitted by an object become more compressed, which is an increase in the frequency as the object comes near and the waves stretch as the object goes farther away. An analogy of this is anything that whizzes by us. Taking an ambulance, for example, imagine you are standing on a sidewalk and an ambulance is about to pass by you. The sound gets more intense as the ambulance approaches you. but becomes less intense as the ambulance goes away from you. This is because of the change in frequency. When the ambulance is going in a particular direction, the sound waves that are emitted by the siren will be compressed in that direction, producing sound of high intensity and high pitch. When the ambulance goes past you, the direction of the compression is now away from you, which means that the sound is now less intense and low pitched. When the sound waves of the ambulance get compressed, the waves become bluer, and when the ambulance passes by, the waves become redder. The waves do not literally become bluer or redder, it is just an analogy that scientists use to show the spectroscopic shift of an object. Since blue light has a comparatively high frequency, compressed waves with high frequency are bluer, and since red light has a comparatively low frequency, waves propagating away from the direction of compression are redder. The same way, using spectroscopy and measuring the wavelengths of radiation from other galaxies which come to us over a period of time can tell us if the galaxy is being redshifted or blue shifted. If a galaxy is redshifted, it means that it is going away from us, and if a galaxy is blue shifted, it means that it is coming towards us. To us, most galaxies, except for the Andromeda galaxy, appear redshifted. Because the universe is expanding and because Andromeda galaxy is on a collision course with the Milky Way galaxy, the distance to the galaxies or any other celestial bodies can be calculated by using the formula V is equals to Hubble's constant multiplied by proper distance. Proper distance is basically the distance at a particular time to the celestial body. Proper distance can change as time progresses. The velocity of the celestial body can be calculated by using the spectroscopic shifts of the celestial bodies that are recorded. Now, when we substitute the values of the velocity and the Hubble's constant, which was initially 500 km per second per megaparsec, then was 180 km per second per megaparsec, 75 km per second per megaparsec, 55 km per second per megaparsec, but now the best current estimate is approximately 73 km per second per megaparsec. A megaparsec is unit of distance. 1 megaparsec is equal to 1 million parsecs, and 1 parsec is equal to approximately 3.26 light years. 73 km per second per megaparsec means that the velocity of galaxies increase by 73 kilometers per second per megaparsec means that the velocity of galaxies increases by 73 kilometers per second every 1 megaparsec. This means that the galaxy speeds up by 73 kilometers per second every 3,260,000 light years. This formula and the Hubble constant were derived by Edwin Hubble after his observations of the spectroscopic shifts of other galaxies.